Hello, hello. I jumped the gun there. Sorry. Hello. Yes. Good afternoon, Vanita. Good afternoon, Brian. Good afternoon, Kaya, with the animated avatar and the scholastic background. Good afternoon, Chastity, with the feline avatar. Good afternoon, Vanita. Is that the word feline? Like as in cat? Yeah. With the floral avatar, which I recall from such semesters known as fall of 2025. Good afternoon, Annie, with the avatar. Okay, with the video, I mean, right. Okay, okay. Hello, we're coming. Oh, and there's Gabriella with the video. Awesome. What? Hello, hello. Why do I call attention to these things and just discourage people from good afternoon, Skylar, with the Avitar. All right. Which I'm still not pronouncing correctly either. Anyway, and what I say? Good afternoon, Vanita. Good afternoon, Brian. Hello, Carlos. Good afternoon, Chastity. Good afternoon, direct chat person. Good afternoon, Gabriella. Good afternoon, Ariana. Good afternoon, Genesis. Good afternoon, Kaya. Good afternoon, Annie. Good afternoon, Natalie. Good afternoon, Sydney. Oh, got an exclamation point out of that one. Awesome. Good afternoon, Mariam. And all caps, got capital letters out of that. All right, awesome. I think we're good to go. I think. Are we? Yes. Oh, and Sydney with the video. Awesome. Thank you. Awesome. It's like, it's like good. Okay. So we're going to do some physics. Whoa, hello. We're not going to do that physics. Yes, we're going to do that physics. Okay. Some logistics first. The homework that's upcoming, I readjust. Someone in the other class reminded me that we don't have John Jay this coming Wednesday, which I neglected to realize. So the homework that was due this Wednesday is not anymore. It's due the following Wednesday, and then the homework after that. So everything got readjusted, but it all caught up with itself. It's all gonna be fine. But yes, you don't have anything new due like an off class day. At least right now you don't. Um, on that logistics, so net, and this I have to say slowly and clearly, I will send you a posting about the following, but so we don't have class this Wednesday. John Jay doesn't have classes this Wednesday. Then next Monday, John Jay doesn't have classes, as you know. Then Tuesday is supposed to be Monday at John Jay. Don't we all love how they do that? Well, yes, we all love how John Jay declares that Tuesday is Monday. But of course, some of us also live in other worlds besides John Jay. I'm sure some of you have jobs um, off campus, or husbands, or wives, or parents, or like whatever. I do. I mean, I don't have a husband, but like what I'm trying to say is somewhat diplomatically, like just because John Jay says that Tuesday is Monday doesn't necessarily mean that the rest of my life cares. Um, so so next Tuesday, when you would normally have this class at 3:05, I cannot teach it. And I feel terrible about that. I will remind you about this in a Google posting, and you'll get points for acknowledging it. Um, but I'm going to tell you right now, next Tuesday, right, a week from tomorrow, when you would normally come to this class online, it won't happen. You will instead watch the video of the section that meets at 12:15, because that one I can't teach. Okay, so I'll remind you of that. It's the same material, all that, just different people. I may even ask you to answer questions about the video. I'm not sure yet, but just please be on the lookout to realize that you won't meet with me next Tuesday, but you will watch the video and be responsible for the material from the other section. And when you get the Google posting to that effect, like you'll get points even just for acknowledging it and sending it back to me. Okay, and many of you know that routine. Um, and then we do have class as normal the following day, a week from tomorrow, a week from this Wednesday. Is that all? Thank God. I don't know which the thank God refers to. And I thank God. Okay. Yes, I'm well, yeah, it's never bad to thank God, so sure. Um, uh, um, okay, so that's clear, I guess. I'll just take it that that's clear. Let me know if it's not. I think strangely, you and I, you mean everybody and I are pretty caught up on homework, which is good. Pretty much all of you have made an attempt and an on-time attempt with homework 1A. I believe you've all gotten points, various amounts of points and feedback. I think all of you gotten feedback on it if you turned it in, unless you like just turned it in. Again, if you didn't get all the points, you still totally can. Probably if you got something in the neighborhood of like 31 out of 35 points or 32 or 30 or 29, it probably means that most of just what's remaining is stuff on question 9, which we're going to start talking about toward the end of today. So once we fully expand on it in class, yet you could go back and redo and submit for the rest of the points. And so the ball may be in my court now to explain all this question 9 business. Um, and once I'm done talking about question 9, that will really help you with homework 2 is like a lot of exercises and practice on the concepts that come out of question 9 on homework 1A. So if you've already started to look at question 2 and it doesn't make any sense to you, you would not be alone. I would not be surprised. Like some of you, it might. And certainly homework 2 is very mathy. So if you've already started to look at it, and it's very calculus-y, but it is like retro engineer, it's like reverse engineering of calculus. So it may throw you off when you first look at it. It'll become more and more clear as we begin to unpack question 9 of homework 1. I mean, that's why it comes after homework 1. So, but now you have like a lot of extra time to do it. So so hopefully that'll all work out. And somewhere in there, we'll discuss homework 1B, but I want to make more tracks before we do. Uh, Oh, so one last thing about all of that. So obviously, if there's any questions or if someone's homework I forgot to grade or something, like obviously let me know in private. But I think that we're all caught up with each other, which is nice. Um, I'm being able to even a little bit stricter about the 5-step method this semester than last semester. Those of you who had me before, that is, yes, I would not only do I mean, it seems like everybody gets it, especially if you had me last semester. It's great. Everybody's doing the steps. They're going to help you more and more as questions get harder and harder, like question 9. But two things to bear in mind. I not only do I want the steps, but yes, even labeling them explicitly as you go, like literally saying step 1, step 2, step 3, super helpful to you and to me. I mean, maybe it's a little bit informal, but it's super helpful. So please do that. I don't think I took off, but whatever, please do that on exams as well. And lastly, especially if we've never been in a class together before, and especially with regard to question 9 of homework 1, which is like sort of my goal to get to today. If anywhere ever on your homework or exams, if I write WWW, maybe I've mentioned this, but that's not a step. Like all the other 3-letter acronyms are particular steps, but that's not a step. If I write WWW, it means what is this? Why is it true? Where is it from? Okay. And really, what that really translates into is one of two things. Number one, it probably means you've dived, as far as I'm concerned, you have dove, you have jumped right into step 4 based on some kind of equation or something that I don't think was properly established in step 3. Or even if you wrote it in step 3, I feel like it's coming out of left field. In other words, often if I write WWW, it doesn't mean that what you're doing is wrong. It might well be like correct, but it's unjustified, it's unsupported, it's unmotivated. So it means I need more explanation and background. Often that might involve some English. And so particularly like in question 9, if you started doing things with cosine or omega or something, that's great. And if you got them from the web, if you got them from past videos of mine, totally awesome. I'm thrilled. And it's not cheating. but it means you now have to explain what it is that you're doing since we've never discussed it before. We haven't established. Okay, now we're going to start discussing omega and cosine, all that, like hopefully a little bit today, and that'll help. But if I say www, it means it needs more explanation. And you want to nip that in the bud now in homeworks, because certainly if I write it too many times on an exam, what that really means is I think too much of this came straight from the web and not enough through your brain after it went from the web or from a colleague. And like you wouldn't want that on an exam. Okay, just saying. Okay, so all right, so I want to get back to trucking through homework 1. I really want, of course, my goal is to get to question 9. However, we did a lot of computations for question 4 and question 5 on homework 1. We did a lot of computations and got correct answers last time. Yeah, stop me if there's any. I think that's all like business to take care of. I mean, I think I'm ready to do physics, but if I'm forgetting something or something logistical or something about homework or points, let me know. But I think I'm watching. I'm looking at the chat. I'm looking out of my side eye. I think last class we did question 4 and question 5, and I guess question 6, and got answers and did a bunch of like equations in math that made it look like we were done. But I think the equations and the math came from a place that needs a little bit of support or underlying explanation. If I'm going to keep insisting from you guys, I need to back up a little bit and explain in a slightly more mathematical way where question 4 and question 5 came from. So again, I don't want to confuse anybody, but the equations that are on the board right now, the top 4 equations, not the one that's circled, everything before the circle, they are equations that I am right now going to, in theory, review. I'm going to like summarize and try to move somewhat quickly through them. If you get lost of like where am I in the material or like what are we talking about, I'm backing up on question 4 and question 5 of the homework. I'm trying to give you the underpinnings of those, the concepts that we really need for this class. Okay, concepts that in theory you saw in Physics 203 or in theory you saw in calculus, but I want to make sure are firm now. So if not, I'm gonna talk in abstract about these 4 equations right here. And again, if it's all old news to you, great. Just take this as a statement of we're responsible for this material for the rest of the class. If it's confusing or new news to you, definitely either mention in the chat or just make a note that you need to ask me more questions about this later and like send me an email or we'll set up a time or whatever. Okay. But I'm going to sort of blast through these 4 equations here on the board, the 4 uncircled equations. And I'm sort of saying we do need to have this material under our belt one way or the other. So either from further discussion. So if enough people email me and say, I didn't understand any of that or whatever, then like I will slow down in the class and explain. But if only a few people do, then I'll just help those few people. So the very first equation. So again, where am I? I'm still in homework 1. I'm back at question 4. Okay. The first equation says that the definition of work. And sorry, please take notes on this. Like I'm trying not to write a lot down because I want to move through this somewhat quickly, but you should. And by the way, some people are already thrilling me. I'm already getting some submissions where people are screenshotting the notes they take in class. And for points, they're doing that, which is great. Let me remind you, if you just screenshot your notes and just put them in the daily turn, that's fine. But if you also put them in the note-taking portal that says, well noted, you'll get more points for doing that. And there's already people, I've never actually seen this before, but I'm so through. Some people are like highlighting or circling the parts of their notes where they wrote things down that I just said, but I didn't write down. Oh my God, does that make a crusty old physics teacher happy? Like, yes. So I'm going to say a bunch of stuff now. I'm not going to write it all down. If you can write it down, Quark bless America. So here we go. The first equation, work in physics is defined to be the path integral of force. more specifically, the work that is done by some force from location x1 along some path to location x2 is the path integral from x1 to x2 of the force. That's what that notation says. Now, let me be a little bit more specific. I'm going to expand this in layers. Um, uh, okay, first of all, like, what does an integral mean? Let me try to remind you sort of quickly. Because if you're like me at this stage of physics, if you are like me, well, I feel sorry for you, but like, get a new haircut. But if you're like the way I was at this stage of physics, I could do integral sum. Like I took my calculus like I was supposed to. I could solve problems. I could do some integrals if they weren't totally unreasonable. But I had no idea what they meant. I certainly couldn't set them up on my own if someone asked me to. I certainly didn't know when an integral was needed and when it wasn't. And I did not see the connection to physics. So I'm just being honest. That doesn't mean that's true of all of you. But like I could do calculus. I had no idea what it was that I was doing. And I knew it. I mean, I was faking it. So a little public service here. When we do the integral from x1 to x2, when we do the integral of force along the displacement from x1 to x2, what we're doing is we're saying that in physical, well, we're picturing, first of all, in physical space, if this is a physics thing, right? Force and displacement, all that, we're imagining that we're walking along some path in physical space from one location to the next. We're taking tiny little steps from x1 to x2. And every time we take a little step, like some number of millimeters or decimeters or centimeters, whatever, we're asking how hard is the force being exerted at this moment? Like if we were watching ourselves push a box along a path along the floor, every step we take while we're pushing that box, we would ask, how hard is our push? And in what direction is our push? Like at what angle on the box is our push? In simple terms, we would take the answer at each step. We'd be like, oh, the push is like 5 newtons. Oh, I just took a 1 centimeter step. And we would multiply those two together. Like we would multiply 5 newtons by 0.01, or whatever I just said. When I say 1 centimeter, by 0.01 meters, we'd multiply the two together. We would throw it in a bag in our brain. We'd be like, okay, force right now is 5 newtons. Okay, the displacement, that the little step I just took is like 0.01 meters. Okay, we would multiply the two together, newtons by meters. We'd get a certain amount of joules. We would store that in our mental pocket. Then we would take the next step, do that again, multiply the force times the displacement, put it in our bag, take the next step, keep on taking these products of force times displacement, keep on accumulating them in our mental pocket. And when we get to the end, the very last position, x2, we'd have this enormous sum of these little products. We'd have a whole bunch of force displacement products, a whole bunch of Newton times meters, a whole bunch of joules, like in our mind. And that would be the total amount of work that was performed along that path from x1 to x2. So first thing I'm saying is, in general terms, what an integral is, particularly if you integrate force with respect to displacement, what you're doing is walking along little bits of displacement and multiplying those little bits of displacement times the force as you walk, and you're adding them all up. That big integral sign is an S, like snake, or more better, like sum. What integral means is sum up all of the little products, and it's always a product on after the integral sign. There's always something times d blah. I'll get to the d business in a second. But always what an integral is a sum of little products. And if it's a definite integral, it means from one place to another. That's always what an integral is. Let me go a step further. The reason we use that smooth, like graceful, elongated S to mean integral is that what we're really doing is taking a good old-fashioned traditional sum like sigma. Remember how in other math classes you use a big jagged Greek letter sigma to mean sum, right? And it's like all intimate. It says like I equals 1 on the bottom, like to n on the top, right? And like we could have used sigma f sub I times delta x sub I. We could have said that to mean sum, but sigma sum means adding up chunks, discrete, quantized, separable products. Sigma is what you would use if you took literally a centimeter step and you had some value of force, and then you took another centimeter step, and then it had some value of force, and then another centimeter, right? That's what, if the sum is discrete, if you could really chop it up into small but finite segments, then we would use a sigma. But, and it would be sigma like F times delta X. But when we take that concept of sigma, of sum, when we take it to the limit as delta x approaches 0, what we're doing is saying, you know what? I want to make these steps that I'm taking so freaking small. I don't want to just step like 1 meter at a time or 1 centimeter at a time or 1 millimeter. I want to take such a small step that whatever the force value is, doesn't even have room to change at all in that step. I want to, like, even if F is like negative kx, even if F is a different value for every single value of x, I'm going to make my step so small, infinitely small, that I catch all the different x values and therefore catch in my pocket, in my products. And therefore I account for all of the different f values. So what an integral always is, whether you're talking physics or not, whether you're talking force or not, an integral always is a sum of products taken to the limit where the second part of the product is an infinitesimally small step of some kind. Dx in this case, rather than delta x. Oh, I think there's something in the chat. I'll look in 1 second. Let me just vomit this out. So really, that integral sign means we've smoothed out the sum of these products and made it into a continuous sum. An integral of any kind is a continuous sum of products. I promise I'm going to look in the chat in 1 minute. I just don't, before this train of thought runs away. Integral is always a continuous sum of products. And the product is always an infinitesimal step along the independent variable times the value of the dependent variable. Always, no matter how complicated integrals look, this is where the whole area under the curve thing comes from. If you're picturing a graph, I promise I'll look at the chat. Not that the chat person's like nagging me, but I'm not going to forget. But if you look, it's like I'm trying to talk about physics here. Like you walk along the path through space and you ask what the force is doing. Well, that's specifically the integral of force times displacement. That's specifically the work integral. In general, you have any kind of function you want. You can always picture the graph where the input of the function is along this axis and the output of the functions along this axis, right? Like the x and the y axis, right? Like, and so this axis doesn't necessarily have to mean physical space. It could mean time. It could mean something else. So when we're thinking about functions in general, like in a calculus class, the whole idea of the integral is you take an infinitesimal step along the x-axis of a graph, whatever it represents, and you take that little infinitesimal step and you look up at what the function's doing. You look at the value of the output of the function, the y value at that step, and you multiply the two together, the input by the output. So what you're doing, if you're on a piece of graph paper, if you're on a graph, no matter what the function looks like, you're taking a step along the x-axis, then multiplying by the value on the y-axis. So you're multiplying the width of a little rectangle times the height of a little rectangle, and then and you're multiplying them together, and you're throwing that little area into your bag, and then you're taking the next step. So as long as the widths of all those rectangles are infinitesimal, then all of your rectangle areas are infinitesimal, and they all add up. Like the area of all of those rectangles adds up perfectly exactly to the area under the curve. I'm just trying to say, and then I will shut up and look at the chat. I'm trying to say, in general, with integrals, why an integral doesn't mean area under the curve. That's a graphical way of thinking about it. But when you say area, and it's correct, I mean, if that helps you think about it that, but what are you doing when you think about it that way? You're thinking about walking along the x-axis of any function and continuously multiplying the x value or the step that you took along the x-axis times the y value. So what you're looking at is the accumulated effect, the accumulated impact of that function along or throughout some space. Bottom line, the work integral is looking at or calculating the accumulated effect of force throughout a physical displacement. Now, I still have like much more to say, but let me pause and look at the let me look at the chat. Oh, this looks exactly like right. Hold on, I'm looking at the chat. Hang on. Oh yeah. Boom, exact. Oh my God. And there's totally a portal for the points for this. I think it's called 1,000 words or something. There's definitely like for putting pictures in the chat. There's definitely a portal for this for points. Awesome. Right. Yes. So I'm just looking again. Right. So the picture in the bottom that thank you, Annie, has put in, the picture in the bottom is the picture of the top. Oh, I'm scrolling as though you can see my scroll. You can't see it, but you can see the pictures, right? Like the picture on the top is a discrete sum. And if you take that to the limit, you get the picture on the bottom, which is the integral. And by doing so, you change delta x to dx. Dx just means difference in two x values, but difference that's so small that it's infinitely small. Like that's what dx means. It just means delta x, as in rise and run, but in the limiting case, where the two values are so close to each other that the difference is not zero, but also not calculable. Okay, that's great, Annie. Thank you. Okay, wait, what was it? Okay. Now, everything I just said is kind of technically just like a reminder of what integrals are, but okay, why am I like saying all this? First of all, if you already always understood what integrals were, but we're fuzzy on the concept of work, then I'm saying what work really is the integral of force times displacement. But it's an integral, right? I mean, it means add it all up. So if the force in this case exerted by a spring is like negative kx or kx, and the displacement is x, some people got this like a little fuzzy in their homework. You can't just multiply kx by x to get the work. You'd have to integrate kx dx, and you'd get 1/2 kx squared. And again, if there's questions about that, definitely email me or text me or whatever. But then second of all, there's one more subtlety before I go on. There's also this business that when you do the work integral, force and displacement are vectors. You notice the vector symbols over the f and the dx. So force and displacement have directions. And we care about their directions. They matter. But at the end of the day, if you think about it physically, when you're pushing a box along the floor, well, two things. One, at the end of the day, to get the number of joules of work that you're doing on this box, joules don't have direction. Like you're not looking for a directional answer. You're not looking for a vector as your answer. You're just looking for a total amount of joules that you put into the box or took away from the box. So you're multiplying two vectors together in a manner that you want to get a scalar as the answer. Well, how do you do that? Well, you look at the extent to which the two vectors agree in their direction. You look at the extent to which you can ultimately discard any details about direction. What do I mean? I mean this. I mean that when you multiply two vectors together in a manner that produces a scalar, that is one form of multiplication. There's different ways that you can perform multiplication when vectors are involved. But when you want to multiply two vectors together in a manner that produces a scalar, what you do a thing called, well, a scalar product, or generally we call it a dot product. You signify the multiplication between the two with an actual dot. Like it's explicit. If you were doing something else, you'd use a different symbol like an X, okay? But here we use it, and this comes up in homework 2 at the end. If you multiply two vectors together in a manner that produces a scalar, what you're actually doing is you're measuring the extent to which the two vectors line up with each other. Because if they perfectly lined up with each other, it would be like if they were perfectly parallel, then you're in effect talking about two vectors that are both lying on the same number line. And you would just be multiplying two numbers on a number line. But if you were multiplying two vectors that were perfectly perpendicular to each other, they have nothing to do with each other at all. You would want the answer to be zero. Let me be. So we use the cosine. I'll be specific about that in a second. But no, I'll be specific about it right now. The sine of zero is zero. If you want to memorize anything about the unit circle, if you don't like the unit circle, or if you get your sines and cosines and stuff confused all the time, first of all, welcome to the club. But second of all, sine of zero is zero. I think I've said this before to some of you. Sine super, cosine crappy, or more or less profanely, sine super, cosine counterintuitive. What by that I mean the sine of zero is zero. And as you open up the angle, as you make the angle bigger, sine gets bigger. Just like the way you would want a function to be if you were inventing the function on a desert island, or at least I would want a function that starts at 0, 0, and then as the theta gets bigger, the function gets bigger. That's what sine does. It's super. Cosine does the opposite, right? When the angle is 0, the cosine is 1. And then as the angle gets bigger and bigger, the cosine goes down all the way to 0, right? That's counterintuitive, but it's exactly what we want here in this situation. When two vectors are parallel, the cosine of the angle between them is a full-bodied 1. So the dot product is the magnitude of one vector, always. This is like a definition. It's triple equal sign. It's like true in physics and in math. In general, if you want to get the scalar product of two vectors, you want to get a measurement of how lined up they are. You do the magnitude of one times the magnitude of the other times the cosine of the angle between them. And this works perfectly for the physics context of work. If I'm pushing a block along a box along the floor, if I'm pushing it at some angle, like 60 degrees from the horizontal, right? Then that means I'm pushing it somewhat horizontally, but I'm also pushing it somewhat down. There's a downward component and a horizontal component to my push. What we're arguing here is only the horizontal component of my push is affecting the horizontal displacement of the box. The vertical component of my push is not transferring any energy to the box or in any way helping the box move forward. So always, when you calculate work, you don't just do F times dx or F times x. You do the magnitude of F times the magnitude of dx times the cosine of the angle between them. Put another way, you multiply one vector, the magnitude of one vector by the magnitude of the component of the other vector that is parallel with the original vector. You only multiply matching parallel components. If I were pushing a box all along a floor horizontally, the entire time I'm pushing, gravity is also pulling down on the box. Gravity is a force in the free body diagram acting on the box. But at no time is gravity helping the box move forward or backwards or anything like that, right? So gravity is pulling down. The displacement is along. They're both there. They're both true. But if I do the dot product of mg times dx times the cosine of the angle between them, I'll get 0, as I should, because although gravity is there and is a force, it is not doing any work on an object that's going horizontally. Okay, so that's the dot product. Pardon me for a second. You could stop me if anything. That's the dot product. So now what I'm trying to say in sum is that technically speaking, we're going to move on to the other equations. Whoa, hello, wait, I just lost. Oh my God. Oh, sorry. Okay, we're going to move on to the other equations, but I just want to make clear that so that technically speaking, work is the integral of the dot product of force with displacement. Here, whenever, so there's a lot of different kind of integrals, right? In math and in physics. Like you could integrate like any kind of function. But if you ever integrate the dot product of a function where independent variable, if your variable of integration is literally dx or dy or dz, like literally referring to some kind of infinitesimal step in literal space, and if you're integrating the dot product of some function with that dx, then that is called a path integral. Like please write that down if you're still with me. Like there's many kind of integrals, but if you integrate, but in this case, like we're integrating the dot product of f with dx, that is called the path integral of f, because f is being dotted with actual space, like as opposed to if the variable of integration were like dt or something, if it was like time or temperature, like it would still be an integral and all that. But if we were integrating, if the independent variable were something else, then we don't call the path integral. But if we're literally imagining ourselves walking along a path and asking what the accumulated impact of the function is along that path, then we call that a path integral. Okay. So, and it comes up a lot in physics, path integrals. So I think some people call it a line integral too. I think it's the same thing, but in my world, we call it a path integral. So, and it's a definite integral, like it has boundaries. Oh, wait, chat. Wait, sorry. So it makes it, hold on, sorry. My screen's all found. Oh, wait, chat. Hold on. Oh my God, it's happening. Wait, I know there's, wait, sorry. Probably good for me to breathe anyway. Wait, sorry. The screen is, okay. Oh my God. Okay. Wait. Okay. So Annie is a step ahead of me now. Okay, so Annie's going to the second equation. Great. Or actually the third. By the way, that let's count that as polite, like let's move forward, Yafferbaum. So she should omit points for that. So yes, I will move forward and get at what Annie's talking about in the chat. Oh, but one thing. Let me just do equation 2 super quickly before I get to equation 3. Why we care about all of this? So summary of equation 1 is work is defined to be the path integral of force. It's the accumulated effect of force throughout some path, right? That's equation 1. That's a definition. The equation 2 is like, why the heck we care as physicists? Why do we care about the path integral of force? Because the path integral of force, double equal sign, turns out to change, or better, transfer kinetic energy. Just to say very quickly, like the reason I care about how hard I push a box throughout some displacement is that by pushing or pulling the box throughout some path of space, I give it 1/2 mv squared. Like it might have already had some, but now I give it more. Or if I pull it opposite to the direction it's going, which is certainly possible, or like friction is acting in the opposite direction something is going, so that if I'm doing negative work, then I'm taking away 1/2 mv squared from the object. So just right, so I'm about to get to Andy's thing, but just let's be clear. Triple equal sign, what work is the path integral of force. Double equal sign, what work does is it transfers energy. to or from a system. What kind of energy? Kinetic energy, 1 f mv squared, right? Okay, now we get to equation 3, what Annie's asking about. Okay, so I'll cut to, so I do have some things to say. All right, well, uh, wait, also, wait, why is the whole screen all messed up? Wait, sorry. Okay, first of all, let me introduce the symbol. Like, well, I do agree with what I certainly like where Annie's going with this, and I agree with what she's saying, but only for certain forces. This is the surprise. What she's saying, that equation 3 makes sense, and she's giving a good reason. But I actually want to say it turns out it makes sense for some functions, but it doesn't make so much sense that it's self-evident. It's actually not true for some functions. So it allows us to make an important distinction. Allow me to explain. First of all, that symbol, you'll notice up until now, I had the integral from like x1 to x2. That's called a definite integral, right? In math, like an integral from a particular boundary to another boundary. Now I've gotten rid of the x1 and x2, and I put a circle through the integral. This is a new piece of notation for many of us. What this is called now a closed path integral. Still path integral, still integrating along some path, but now it's a closed, and this is the part Annie clearly does understand. I mean, she's anticipating, but I'm saying in general now, piece of notation, if you ever see a circle on a single integral, then we're still talking about a definite integral. It still can be evaluated in some specified region of space or some specified chunk of the x-axis. But it now referring to what you might loosely call a round trip. If you have a circle on the integral, what we're saying explicitly is, imagine that you integrate from somewhere to somewhere, but then you integrate your way back home, that you end up where you start. That is called a closed path integral, like always in math and physics. It's a definite integral for some kind of round trip in one dimension. That I'm saying that loosely because it's not like really round, it's all in one dimension. But if you end up where you start, that's called a closed path integral. Now, here's the Annie part, or here's the interesting, seriously, here's the surprising part. One might think that if you did that with any function, you would always end up with 0. Like you figure, like whatever you do out, like you figure you undo on the way back in. But it turns out that's not the case for all functions. For example, it's totally not true. Like when I say it's not true, I mean the closed path integral for just any random it's not true for all functions, and specifically in physics, it's not true for all forces. There are many forces for which if you perform the closed path integral, you will actually not get 0. Now, that is surprising. I mean, this is the Annie point. Let's look at friction, for example. I'm pushing this box along the floor, like pushing. While I'm pushing it, imagine that there's friction from the floor. So friction's pushing against it, right? So I push the box like 5 meters. And let's say during that time, friction exerts a force of like negative 10 newtons, right? Okay, but the box is going this way to the north, let's say, and friction is pointing back the other way to the south, right? Like that's how friction works. It goes against the motion of an object, right? So that's not a surprise, right? But so that means you have force going in one direction, displacement going in one direction, force going in the other. So one of them is getting a positive sign and the other is getting a negative, no matter how you define your axes. So you have a negative times a positive, and that means friction's doing negative work on the way out. Now, still not a surprise, right? But that means on the way out, while you're pushing the box, friction's doing negative work, i.e. taking kinetic energy away from the box. If all other things are equal, it might be slowing down the box while this is happening. Still not a surprise, maybe. But now on the way back, if you now let the box come back because you're pulling it or you're doing something, which is fine, now on the way back, the displacement flips its sign, but so does the force. They both flip, right? You're coming back the other way, and so friction goes against that. So you still have a positive times a negative on the way back. Friction's still doing negative work on the way back, and the math work, like whether you're thinking physically or mathematically, the work on the way out done by friction is negative. So say it was, like we said, like negative 5 newtons. I forget what it is, negative 10 newtons times 5 meters. So negative 50 joules on the way out. It's going to be negative 50 joules again on the way back in. Friction will do a total of negative 100 joules of work. And you know this is true because if you did this whole thing on a carpet, the box would heat up a lot on the way out and it would continue to heat up a lot on the way back. You generate a lot of heat, right? Now you might be saying, wait, but that only all works if we're like pushing it the whole time. Like friction can't like make the round trip happen. Sure, I don't think friction can make the round trip. So let's look at what your hand is doing the whole time to push the box out and to pull it back. Your same logic applies to your hand, only in both cases, what the normal force from your hand or what the tension from some string is doing is always positive there. It'll be positive times a positive on the way out, and then it'll be a positive times a positive on the way in. So when I'm arguing, and I'm going to pause for a second, like to see if this is clear to Annie or anybody else, I'm saying that forces don't automatically do zero work around round trips. In fact, all customary contact forces, such as tension in the string, normal force from a surface, or friction, they all do, or did I just say that twice? They all do they're all non-conservative. They don't conserve. They don't do, like the minus signs, in other words, don't work out. Even though you've integrated along a closed path, you end up with a net effect of energy gain or energy loss. Now but some forces, it does work out, like gravity. Gravity, same scenario, right? Say you just throw something up, it goes up to a height h. So you throw some mass up to a height h, and then it comes back down to the ground, right? You just throw it up and it comes back down. Well, on the way up, it's displacing positively, uply, but gravity's pulling down mg. So on the way up, the force is negative mg, let's say, and the displacement is h. So on the way up, the work is negative mgh, right? And again, that makes sense because on the way up, the thing is losing kinetic energy, it's slowing down. But then it starts to come back down. Now here's the key, is gravity doesn't flip direction the way friction does. Gravity is always pulling you to the earth. Friction is not. In mathematical terms, gravity somehow cares about where you are, position, whereas friction seems to care about your velocity, the direction of your motion, right? They're very different. So gravity just cares where you are. It doesn't care where you're going. So the force is negative mg, whether you're traveling up or you're traveling down. So on the way up, the work being done is negative mgh. You're losing kinetic energy, slowing down. Then on the way back down, the work being done is positive mgh. So yes, you're going down, but now the two signs agree. The force is down and the displacement is down. So whether you call them both negative or you call them both positive, they're both. So on the way down, the work being done is positive. So now you gain back kinetic energy. And of course, the work is the same on the way back down as it was on the way back up, except for that sign flip. That honestly, and again, I'm not saying, I mean, I'm totally like applauding Annie for like putting that, but like what we all would be thinking if we hadn't like work this through. You would think that would sort of like always happen, that there'd be a minus sign in one direction and not in the other. But no, it depends what kind of force, what kind of function we're talking about. If it's a function like gravity, then that happens. And we call that a conservative force. When the closed, so the technical mathematical definition of a conservative force is which will from here on in like denote as F sub C. An F sub C is one for which the closed path integral is always zero. Such examples include the elastic spring force, negative kx, the gravitational force, like I just did that example, whether you're talking about mg or gmm over r squared, and the electrostatic force, which is a big thing in this class. Is sort of why I'm talking about all of this, because soon we have to get to the electrostatic force, and you'll see it works just like gravity in that respect. Those three forces are conservative. Note, and specifically because mathematically, the closed path integral for each one always yields zero on an intuitive physical level. If like I'm losing any of you in all the like integral language, if you think about it, what's in common about those conservative forces is that they all sort of have some kind of equilibrium position or orientation associated with them. Like gravity is always pulling you to the ground. A spring is always pulling you to its center. Protons are always pulling electrons like toward them, right? That's an informal thing to say, but that is not a coincidence. When a force is specifically dependent on position, then it's generally a conservative force. If the force, and there's generally an equilibrium position that we recognize with that force. And when not, then not. So tension, friction, normal, not conservative. Gravity, spring force, gravitational or electrostatic force, conservative. We have 25 more minutes. Hold on. Wait, so honestly, and not to be weird, but just to totally acknowledge because I love I mean, Andy, if I can, I'm not looking, but is that does that address what you're saying? Like, does that jive?
Yeah, it jives.
Why should I? Okay, I won't call. Okay, all right, cool, cool. Okay, I don't know what jive means either. Okay, okay, but it's a great question. Okay, so why do we care? Why does she care? Why do I care? Oh, I'm paid to care. Why do you care? Because that's so not true. I whatever. Okay, why do we care? We care um because then, so I'm going to equation four now. Now, again, what am I trying to do right now? I'm just kind of trying to tell you guys stuff that you've heard in physics before, but I'm trying to link it formally to the math. And or for some of you, I'm trying to talk about math things that you've heard before, but give them like a physics like pulp to hold it together. Whichever. So I'm saying from now on, what it means to be a conservative force is for your closed path integral to be zero. But then but that gives us a huge advantage. If we know that certain forces will do no work, definitely, over a closed path, that means we can save ourselves a lot of hassle. Instead of constantly calculating kinetic energy losses and gains as we go, instead of over and over doing the work kinetic energy theorem of equation number two, we can in effect make a prediction. We can say, as you have before, or you did in seventh grade or something, we could say, look, when we throw something to a height h, when a mass gets to a height h and it temporarily stops, like it's at the top, it has velocity zero, right at that moment, it has no instantaneous speed, so it has no kinetic energy, right? But we know that gravity did, and the reason is because gravity did all this negative mgh work on it, so it sucked all the kinetic energy out of it, doing all this negative work on it, right? And now the block or the mass is up at the top with no kinetic energy left because of all this negative work that was just done on it. Well, we could wait for it to come back down and then calculate the kinetic energy that's going to be gained when it comes back down. And that we could do that, and that's fine. But or we could say we know in advance. We know it negative MGH work was done on the way up. We know that if and when this thing ever comes back down to where it started, we know that all of that negative MGH must be unwound by a positive MGH because we know gravity is a conservative force. So we know that the net effect on the energy of this object by the time it returns to its original position, say its equilibrium position, we know the net effect will be zero. It will be no energy gained or lost by the time it comes back. So why don't we save ourselves the hassle and just say that when the thing is at the top, even though it has no kinetic energy at all, I mean, it has no kinetic energy at all. Let's say it's storing its energy in the form of potential. It's like a little, you know, flower waiting to blossom or whatever. Like, let's say that at the top, even though there's no kinetic energy, the block is storing energy in the form of potential. How much energy is it storing? Exactly the amount of work that the conservative force will do to bring it back from this arbitrary position to equilibrium. So we're saying from now on, every trip, every one-way trip under the activity of a conservative force, every one-way trip can be viewed as the first leg, as the outbound leg of a round trip. And as long as we know what happened in the outbound leg, we know automatically what's going to happen on the inbound leg. So we can from now on say that things are storing potential energy whenever they're not at equilibrium. And the potential energy that they're storing is literally the amount of kinetic energy they'll get back, the amount of work that the conservative force will do to bring them back from that arbitrary position x naught to the equilibrium position of zero. So we invent this idea. All of physics could be done. We could believe in a whole universe and never have to believe in potential energy. It's just to be a lot more computations. And when we say that the energy is being stored, you might ask, where's it being stored? Is it being stored in the box? Is it being stored in planet Earth? I say it's being stored in our mind. It's literally just, I'm not saying it's like not true, but I'm saying it's a construct that we came up with to shorten our computations. So that at the end of the day, we're just about to ready to go on, at the end of the day, we can say that as long as the only forces that are acting on an object are this kind that gives back everything it takes away on a round trip, as long as they're only conservative forces, then we could say at any given moment, the total amount of mechanical energy that an object has is all of its kinetic plus all of its potential. Because the potential is just bookkeeping prediction of the kinetic that's been lost so far, but will definitely come back once this thing comes to equilibrium. So that's why we can say for any two places in any kind of journey under conservative forces, for any two places, the sum of kinetic and potential has to be a constant because, again, we can say this only if all the forces doing work are conservative, because that means we know anything that got taken away will be given back. So kinetic plus potential is just a way of saying all that you have plus all that you're going to get back. And that amount will never change because the total work that will be done, if it's only conservative forces doing work, will be zero. Okay, wait. Oh, sorry. Is that a voice or is that wait, did I just, I'm looking at two different screens. But no, you good? Yes? No? Okay. Now, again, that was like a big, I'd like you to know those concepts. What's a takeaway here? Like what the takeaway is, please know the symbol for a closed path integral. Please know the concept that a conservative force is one for which the closed path integral is always zero. Please know that potential energy is the amount of work that a conservative force would do to restore something to equilibrium. Oh, and that's why there's different conservative forces for different, there's different potential energy functions for different forces. Like for gravity near the surface of the Earth, it's mgh. Okay. I'll just finish the sentence and then, like, that's the integral of mg dy from 0 to h. Or why the potential energy of a spring is 1 f(kx) squared, because it's the work that the spring force would do to bring you back from x to 0. And the work is the integral of kx dx. So you get one. So different conservative forces have different potential energy functions. So you don't memorize. That's why if anything, you just memorize equation 4, and that's how you get them. Okay, sorry, Annie. Yes.
Oh, two questions. So for the first one, I'm looking at your equation number four, and then I noticed that for the bounds of the finite integral sign, you have x naught to zero. Is that what it is?
Yes. Good question.
And is there a reason why like for like for equation one you have like x sub one, x sub two, but then like here you switch it up?
Yeah, that's a really good question. And yes, really good question, good observation. And yes, this happens not to be a typo. Yes, in equation one, I'm saying any two arbitrary spots from here to there. And one of them could be an equilibrium position or not. Like, I don't even know about equilibrium when I'm doing equation one. It just says in general, the work from here to there is a path integral of the force from here to there, wherever here and there are. But then in equation 4, now I'm talking only about integrating conservative forces. So two things are now happening. number one, if I'm talking about a conservative force, now I have a definite idea of an x equals zero, like a special place called x equals zero, which is the equilibrium place. The place where, according to all of this analysis, the place where there would be no potential energy, right? So first of all, like zero now has significance that it doesn't in general for equation one. But then second, and this is definitely, I think, part of your question, a good question, is I am specifically integrating. Oh, and what do I mean by x naught? For x naught, yeah, I could have used x1 or x2 or something, but I'm sort of intentionally calling it x naught so that you don't think it necessarily has to be either of the two positions from equation one. It just means some like known location x naught, maybe where the whole experiment began or something, but some known location that is not x equals zero. So for in the spring problem, like right, like it's it's x equals 15 centimeters away from the center, or in a gravity problem, x naught might be like height h above the ground, but it's some arbitrary location that is away from equilibrium. And what I'm specifically arguing here in this definition is that the potential energy function is how much work the conservative force would do to bring you from this unstable place to, well, I should say, to the stable place of equilibrium. Like I mean, I'm really glad you asked because it really matters. I'm actually integrating from x naught in the direction toward zero, because what that will do is minimize minus signs. It like literally means I will integrate the force in the direction that the force would have to act to restore everything to equilibrium. I'm making a prediction of how much work the force will do to bring everything back to equilibrium. So it'll be like a positive times a positive, and I'll get like a positive answer. That's why we can say at the top of something like the potential energy is literally positive mgh, because that's how much work gravity would do on the block to bring it from h down to zero. Does that make I'm looking at you.
Yeah, yeah, I think I'm getting it now.
Are you being okay? Okay, so you let it sink in. But she's right to I mean, anybody, please, and it's not just about, I mean, it's about anybody who asks anything. These are, and again, well, I mean, I'll move on in a second, but you can always, all of you can go back and ask this later too. Again, what am I really just trying to do here? I mean, I'll move on. I know it's all very abstract for many of you because I'm not like literally explaining a homework problem. I'm going to go to homework for the next 13 minutes. I'm going to go to question 9. It'll, in a way, be more concrete. But if nothing else, for all of you who are trying to get this, either think of what I'm doing as I'm trying to give you more mathematical language for the physics you kind of already can picture, or I'm trying, wait, or the other way around. Like whichever you think is more clear in your mind, all of you, any of you, if you kind of think you're got the math, but you've never really, then I'm saying the physics matches these math concepts. But if you've never really been comfortable with calculus, and that was me, anyway, whichever one it is, think of this as I'm translating between the physics and the calculus notation. But okay, but it'll become more concrete as we go. Now I know there's only 12 minutes. I'm gonna totally shift gears now, unless there's any. Well, are there any other questions on that for the moment? I know it's abstract. Any other questions on that? All of it and nothing else, all of that was like to justify where one F, well, it's to justify where one F mv squared plus one F kx squared over here equals one F mv squared plus one F kx squared over there, like where that came from in question 4 and question 5. And yeah, I mean, I should probably write this out, but I'm not going to now. 1/2 kx squared is the integral of kx dx. That's what that is, right? Like, I could rabbit hole on that for hours if you want me to. But like, where did 1/2 kx squared come from? It's the work that the kx force would do to bring something, a displacement of x. Why the 1/2? Because when you integrate kx dx. You get 1/2 kx squared. Why does that physically make sense? I'll say this very quickly. Like, why is it 1/2? Like, why isn't it just kx times x kx squared? Because the whole point is that at every value of x, f is a new value, right? If we literally said that the work done by a spring is literally kx times x, that would be a lie. Think about where, if the mass is at position 0.15 meters, as it is for this homework problem, it starts at 0.15 meters. Well, sure, at that moment, the force is 200 newtons per meter K times 0.15 meters. Sure, at that place, the force is 30 newtons. The magnitude of the force is 30 newtons, right? But we wouldn't want to multiply 30 newtons. I mean, you might want to, but it'd be wrong to multiply 30 newtons times 0.15 meters if you're trying to calculate the total work that the spring does to bring the mass all the way from 0.15 all the way to zero. It would be a mistake to multiply 30 newtons by 0.15 meters because the 30 newtons is only true right at that first position. Really, right? The whole issue here is that force is changing at every position. Like, that's why we're analyzing a spring to death for weeks, because it actually raises a lot of interesting issues that the force is changing continuously with every position. So if we multiplied 30 newtons by 0.15 meters, that would literally be just as wrong in a certain direction as multiplying by zero, by multiplying 0 newtons by point, right? Because that's what's happening by the time the thing gets all the way in to equilibrium. Now the force is zero. So why wouldn't we multiply zero by 0.15? That would be very wrong. And multiplying 30 by 0.5 would be very wrong. So what is correct is the average of the two, is the two values added together divided by 2. Oh, it works out perfectly. Technically, because we integrated and got that 1/2, but it actually spits out a value that actually, really, if you think about it, is the average value of force times the whole displacement. If you call what I just said at all, first of all, quark bless you, right? I'm trying to just, right? So I'm saying work done by a spring, therefore potential energy due to a spring, is the integral of kx dx, which is really 1/2 kx squared. And what I'm trying to argue here is that 1/2 comes from calculus, but it makes total sense because what it's really doing is it's saying we use calculus when things are varying, and we get the 1/2 because we're really saying we better average out the force is the maximum force and the minimum force if we want to capture all of these different forces that are occurring. And if you really got what I just said, then you might be thinking, well, then frick, why don't we just do averages all the time and stop the calculus madness? Great question. If you're thinking that at all, even like 1% unconsciously, if you're thinking, I kind of get what this madman is saying, but then it seems to me, why don't I just freaking do averages and be done with calculus? The answer is the average worked perfectly because this force is linear. But the minute any force is more complicated than linear, then a simple average won't work. What integrals are is a way of capturing averages in all kinds of complex situations. That is what we're doing, if that helps at all. Okay. But sorry, is that, oh, Annie, sorry, go. And then, yes, Annie.
You're talking about like a 1/2 component. Can you like it might be a dumb question, but like can you like explain it? Because I'm not seeing it. Like where is it?
Not a dumb question. Okay, no, it's not a dumb question. I'm just here. Wait, well, okay. Hold on, I'll do this quick. And I'm watching the clock. I know there's, hold on. Sorry. Uh-huh. Okay, I'll do it right here. I'm just trying to move the page, but okay, here, I'm saying this. Okay, if I want to know the work that a spring does on a mass to go from some point x naught to zero, right? Um, right? The force, so I have to integrate the force with respect to displacement. The force is negative kx, like the Hooke's law force. And stop me if I mean Annie or anybody else. To stop me and if this is if the time runs out when we're done with it, it's fine. Like we'll get to the other stuff next time. Like this is totally worth it. So yeah, we have to integrate this. Well, first of all, you know from integration, I can get rid of that negative sign by flipping the limits. And if you don't know that, we could talk about that later. But um, so now, but it's because it's subtraction. It's like multiplying by a -1. But all right, so this is the integral I have. The integral from 0 to x naught of kx dx. I'm going to the next page. So work equals the integral from 0 to x naught of kx dx. Well, the variable is x. So k is the constant. It comes out of the integral. Now, this assumes that people sort of remember their calculus, but so I have the integral of x dx. Now, what is the integral of x dx? Well, the way I think of it, and maybe this is a whole other lecture we can have if everybody wants it, but the way I do integral like that is I do the derivative backwards, right? I believe the fundamental theorem of calculus. I believe that the integral of the derivative of a function is the original function itself. In other words, I can do the antiderivative using the power rule. I could do the power rule going backwards. Now maybe I'm saying this too fast for some people, but I think the derivative of if I have the function y equals x squared, I believe the derivative of that is 2x, right? Like I multiply the whole thing by the power and I lower the power down by 1. That's the power rule for derivatives. Well, if I want to do integrals, I do that backwards, right? So I raise the power up by 1 and divide the whole thing by that new power. In other words, I get kx to the 2 over 2, and I evaluate from 0 to x naught. So I get k, like if this were just a calculus problem in math class, and that's the one. So I'm saying the work that a spring does to bring a mass from some arbitrary position x naught into the equilibrium position, the work that the spring does is 1/2 kx squared. And now I'm saying, therefore, that's the potential energy function of a spring. If that's the work, that's how much energy the spring will give back to the mass as the mass comes back to equilibrium. Therefore, even if the mass is just sitting there held, that's how much energy it lost on its way out. So that's how much it's storing, 1/2 kx squared if it's sitting at position x naught away from 0. And what I'm trying to argue to everybody is that 1/2 is the part that is surprising. Like if you didn't know any of that and you just thought work is force times distance, you'd go, okay, the force is kx, the distance is x. I guess I'll do kx times x, kx squared. But I'm saying, no, you have to take into account the fact that the force is changing the whole time. That's why we do an integral. That's why we get a 1/2. Okay, that's a lot. But wait, Andy, did that answer or no? Oh, wait, I'm looking.
Oh, yeah, yeah, for sure. Thank you.
Oh, for sure, even. I got it for sure. Okay, awesome. Okay. So that's good. I hope that helps other people too. Again, if it was totally off the topic, I wouldn't answer it, but I think it really is the topic. So now I know we only have 2 minutes, so I'm just going to tell you what I'm gonna give you these notes anyway. I mean, I'm post them, but what these notes were on question 9. And don't worry, even in these notes, I still didn't finish it. We're still going to expand this slowly next week, question 9, and then we'll finally be done with this sheet, which I'm sure you want. Question 9 is now saying, look, at time equals 1, what's the position? What's x? Very straightforward sounding physics question. But you notice all of the work we've been doing up until question 9 has all been grappling with this new idea that now space x has become our independent variable for a spring. Like everything depends on x. Now we're shifting gears to old physics and saying, but how does it depend on time? And no one's told us that yet in this problem. Right? That's the challenge. How does this depend on time? We're looking for some function of time like x equals 1/2 at squared plus v naught t is a function of time, but that one won't work because that assumes constant acceleration. And our whole thing here is the acceleration is not constant. So what do? if we're solving question 9. Now, again, I will talk more about this next week. I know it's a very hard question. A lot of you don't know how to like finish it or get a correct answer. That's totally understandable. But here's a place where totally you can do the steps and get very far into the problem and see things that you didn't know before. Step 3, what do I actually know? Whatever equations are on the web, the web knows them. What do I know so far about the universe at this stage? I know F net equals ma. I know that in the spring force F equals negative kx. I know I have like 60 seconds left. And I know that the definition of instantaneous acceleration is the second derivative of position with respect to time. That I know. That's my step 3. So step 4, I put them together for a spring. I put them together and I say, okay, I say, and I divide both sides by m. I say d2x over dt squared equals negative k over mx. Everything, okay, it's 4:20. I'm just about to wrap up. If you have to go, go. I won't be insulted. I'm just about done. But I'm saying K and M are constants. They're not variables. All the other variables are in place there that I'm looking for. It's treating X as a dependent variable, T as an independent variable. All I need to do now is like unpack this package and get literally something that takes T as an input and spits out X as an output. I don't know how to do that yet, but I know this. That statement in white means I need a function that when you take two derivatives of it, when you differentiate it twice, you get back itself times some constant times -1. Well, I'm going to guess and check for right now. I'm going to guess the function cosine. First of all, I mean, the thing is going back and forth, back and forth. The mass is going back and forth smoothly in a way that reminds me of cosines. But why else am I thinking of cosine? I'm just guessing. It's not a proof. I'm guessing cosine because if you take one derivative of cosine, you get negative sine. You take another derivative, you get negative cosine. Oh, when you take two derivatives of cosine, you get back itself times -1. That's the type of function we're looking for. So it's some kind of cosine. Then I guessed some constants. I guessed, but I checked them. And this is the whole point of all of homework 2. I'm saying this very fast. I'm just about done. I'll explain where my guesses came from next week. But yeah, but you could guess it too if you think it through. But if you put an x naught before the cosine and an egg because of units, basically think about units, then you take two derivatives of that with any basic calculus you already know, chain rule, whatever. Take two derivatives of that and you will get negative k over mx. So that shows it's right. You have to think of units to guess it, but then you check it by taking two derivatives and it's right. So then you plug in the values that you have and you'll get 0.116 as the answer. I will talk a lot more about that next week. Don't worry if some of it went over your head or whatever, but that's a basic idea of question 9. And it's a basic idea of most of homework 2 is retrofitting derivatives. It's called differential equations. Okay, you've been very patient. Sorry, it's 4:22. I will hang out if anybody has questions, but you certainly don't have to. Thank you for being so patient. Obviously, I'll post these notes. Okay, we have a good day. Yes, and have a great week. Okay, I'm turning off the recording.